Unit 3 is talk about thermal chemistry. I mean, generally, we're just scratching the surface of the thermal chemistry. I mean, thermal chemistry is to be honest, I think it is the most hard part for chemistry student, because thermal chemistry is involving too many calculations, too many equations. Okay, so that's why I think I said thermal chemistry is harder than the unit 2. But generally, we're in the Chem 1 class, we're not talking too much on the thermal chemistry. So you'll still be able to handle it as long as you practice. Okay, you should be able to handle it. And then we're going to talk about the gas, the property of the gas. So that is the unit 3 content. Okay, yeah, thermal chemistry, a lot of calculation, but at the beginning today in this class, I'm going to talk about the concepts. Okay, you need to understand the concept, and then we're using those concepts to involve in the calculations. So the first concept, we need to understand the difference between system and surroundings. By definition, for system is talk about the universe that you observe. That we observe. Yeah, so what does that mean? The universe that we observe, that means system. So that's really just depends on, okay, what the scientists try to observe. Okay, for example, if you're talking about, we try to figure out what happens inside of this container, and this inside of this container is the universe that we observe. So that's going to be the system. Okay, so but if I want to observe what happened for this room, and this room will be the system. Okay, yeah, so that really depends on what you observe, and then you need to, then you define what is the system you're talking about, right? Okay. So surrounding is talking about the rest of the universe other than the system. Okay, the rest of the universe other than the system. Okay, so that's the difference between system and surrounding. In other words, system and surrounding is coupled together. Okay, so if we have a pie over here, if one part of is a system, and the rest of the others will be called a surrounding. Make sense, right? Yeah. So if we observe what happens, the inside of this container is a system, then the rest of the others, not just the rest of this room, maybe rest of this building, maybe rest of the whole earth, maybe rest of the whole universe is called surroundings. Are you clear? Okay, so that's the difference between surrounding and systems. Okay, surrounding and system. So that's the difference between surrounding and system. The next part we're going to talk about, so what exactly is energy, right? Then we need to talk about energy. There are several different types of the energy. First, I'm going to talk about the energy that focus on in this class, in this thermal chemistry. since it's called thermal chemistry, so the energy we talk about, this is heat. Heat is a form of energy, but this energy is used only changing the temperature. So heat is the energy that is used to change the temperature. Change the temperature. Okay, so if we absorb the heat, the object will increase. If we release the heat, then the object's temperature will decrease. Okay, so you decrease the temperature, then that means the heat, part of the heat is being released. Okay, if you absorb the temperature and then absorb the heat, so the temperature will increase, just like you're trying to boil the water, right? When you boil the water is constantly absorb the heat from the stove, and then the temperature of the water will increase. So that is the part of the heat. Okay, they're absorbing the heat, so the temperature of the water will increase. Are you clear? So that is the form of energy. The other energy in chemistry we'll also talk about is a kinetic energy. The kinetic energy generally is energy that is used to move the object. So in the chemistry, we're not talking that too much, but one of the concepts we talk about is the kinetic energy of the molecules. Okay, the kinetic energy of gas molecules. So, I mean, right now you cannot see the gas molecules, but I mean, gas molecules is everywhere. Okay, right? Yeah, it's very small, like oxygen molecules, okay, hydrogen molecules, CO2 molecules, nitrogen molecules is everywhere in this room, but you cannot see that. But those molecules is not just stay there; they are actually moving all the time. Okay, the gas molecule always moving, even there's no wind, it's still moving. Okay, it's just flying everywhere. Okay, it's flying everywhere. So that is why, I mean, we are using the kinetic energy is to represent how fast or what is the energy of those molecules that can move. Okay, yeah. So that is why in the chemistry, a lot of cases, it's better if you want to understand the property of the gases, the property of the solids or liquids. The most of cases you need to think about those the molecules in the micro scale, in a smaller scale, pretty small scale. For example, you can think about it. You can imagine that the gas molecule actually, I see one of the gas molecule, they're flying everywhere. They're flying everywhere. They're just moving around in front of your eyes, but you cannot see. But you can imagine that, right? So that is the gas molecule. What happened? And that's the kinetic energy that we're talking about. Okay, yeah. The next energy we also talk about is the potential energy. The potential energy. Well, we know when we talk about physics, potential energy is talk about the energy that's stored inside of the object, right? Or I'm holding this pen, but if I release it, the pen will fall down. So this pen has the potential energy there, right? But when we release it, it will fall down, which means the potential energy is converted to the kinetic energy. That makes sense, right? Yeah. So that is potential energy. But in the chemistry, when we talk about potential energy, we're not talking about potential energy in this way.
And most of cases, we're talking about potential energy that's stored in bond, stored in chemical bond. Okay. In chemical bonds. So that is the potential energy that we talk about. So that is why you can using the fossil oil, fossil fuel, okay, to fossil energy to burn it, right? One is getting burned. They actually, the chemical reactions make the molecules re-bond together. So reorganize their structures. And then some of the chemical bond will be broken. And meanwhile, when they broken, and then they start to release a lot of the heat. And those heat will be converted to the other form of the energy. So that is why you can have your car to move. Okay, so those energy stored in the chemical bond is the potential energy that we're talking about. Okay, so just to let you know, we have those several forms of the energy. Heat is the most case we're talking about over here. And then the heat has a flow, has a direction of the flow. So let's talk about the flow of the heat. Let's talk about flow of heat. Okay, so the heat is transferred, is moving around. It's not just stored somewhere and never leave. Okay, yeah. So the heat flow is always moving
from the higher temperature to the lower temperature object. So for example, this guy is 80 Celsius and this one is only 20 Celsius, then they're going to move. Okay, the heat will move from the 80 Celsius object to the 20 Celsius object. It really doesn't matter how the size of this object. If this object is 100 Celsius, but this one only like 15 Celsius, they are still going to the heat flow still going to move from the smaller object to the higher object. It really doesn't matter what the size of this object. Okay, it just depends on the temperature of the object. Okay, it's always moving from higher temperature to the lower temperature. Okay, so this is a transfer of the heat. Okay, so again, heat is the energy. And we talk about energy is never being created or destroyed, which means the energy will be transferred from one side to another side. Okay, so if something got released the heat, that means the other object will be absorbing the heat. That makes sense, right? Yeah. So this 80 Celsius object is releasing the heat, and meanwhile, this 20 Celsius object is receiving the heat. So one is giving out, the other one is receiving. The total amount of the heat should be the same. Does it make sense, right? Total amount of heat should be the same. Otherwise, that's going to be destroyed the rule, thermochemistry law. All right, so this is talking about the flow of heat. So I'm talking about the real case. Once you open the refrigerator and you feel cold, then what is happened? What is the direction of the heat? Once you open the refrigerator, you feel cold. Yeah, so that means your body actually the heat is being sucked by the refrigerator. The heat is being sucked. So you're releasing the heat and the refrigerator absorbing the heat, right? You continue to release the heat and the refrigerator is receiving the heat. Okay, yeah, so that's why we need to wear clothes, because our body is constantly releasing the heat. Okay, the clothes is helping us to prevent the, we're still going to release the heat, but we're going to decrease the rate of the releasing the heat. Okay, otherwise you're gonna constantly eat the food, okay, all the time, because your body is constantly releasing the heat. That makes sense, right? Yeah. All right. So generally, that's a flow of the heat. Okay. Yeah. So that's why we're going to talk about the one of the concept over here is called the endothermic and the exothermic process. So the endothermic and exothermic could be, those two different. Endothermic is generally is talking about where this object or the system is going to release the heat. And then the surrounding is going to gain the heat. And the endothermic is go opposite way, which means the system gain the heat and the surrounding is going to release the heat or lose heat. Okay, so this is what happened for endothermic or exothermic. Okay, yeah. So the really is just depends on what's the system you're talking about. Okay, the system you're talking about. For example, okay, right now our body is constantly releasing the heat. Okay, our body is constantly releasing heat. And then if you think your body is as a system, then what is the process it is? That's going to be an exothermic process, because your body is a system and you constantly releasing the heat. So that's an exothermic process it is. But if you think, is this room other than your body, then what happened as a system? If the room other than your body as a system, then the system actually is the endothermic process, because the system is constantly receiving the heat from your body, right? Then in this case, the room other than your body is a system, and your body will be a surroundings, right? So in this case, the room will be a endothermic process, and the surrounding will be, the room will be the endothermic, because we all talk about system. Are you clear? So when we talk about endothermic or exothermic, you really need to determine what is the system it is, right? If the system is the end that's receiving the heat, then that's an endothermic process. If the system is the parts that are releasing the heat, then that's gonna be the exothermic. That makes sense, right? So one of the cases, you are burning a wood. You're burning a wood at your home, okay, in the stove. No, it's not stove. How come we're burning a wood? Okay, you're burning a wood in the fireplace. Okay, then for the wood, what do you think? Is an endothermic process or exothermic process? What do you think? For the wood, if you're thinking wood is a system, that's gonna be the exothermic, because you burn the wood and the wood start to releasing the heat, right? Yeah, you think about it. It's releasing the heat, but where the heat is from? Coming from the wood, right? And the wood actually is storing quite a lot of energy inside, so the potential energy, right? And you think about it, when you burn the wood, after the burning the wood, what's left over? ashes, right? It's only just ashes, which means all the potential energy is released, nothing left. Only the ashes actually only containing some of the metals, some of the salt, like maybe potassium, sodium left over. Those are the stuff that you cannot be burned, right? So the heat is being released. So that's why nothing left over. That makes sense, right? Yeah. So this wood is the exothermic process. But how about if you're standing by around the fireplace, you feel heat, right? Feel hot, warm. And for you as a system, what happened? What is process it is? That's going to be the endothermic, because your body is continue receiving the heat from the wood. That makes sense, right? So again, endothermic and exothermic is really depends on what's the system you're talking about. Okay, yeah, what kind of system you're talking about. That makes sense, right? Yeah. So this is an exothermic and endothermic. So we're going to talk about some of the like a phase change. What the phase change will affect the endothermic or exothermic? Phase change. So, I mean, there are 6 types of the phase change, right? The phase, we're talking about solid, liquid, and gas. So if you want to think about, okay, which one has more heat, then you just think about the temperature of those states, right? Think about the temperature of the water. As a solid, ice is below 0 Celsius, right? Liquid water is from 0 to 100, and the gas must be above 100 Celsius. That makes sense, right? So that means, okay, which one has more heat? Gas should have more heat, right? Yeah, gas, because gas has a higher temperature, so the gas should have more heat. So that means everything from higher temperature to the lower temperature, those are all, what do you think, the processes from higher temperature and to the lower temperature phase change is going to, you're going to release the heat out, right? Because gas has more than 100 Celsius for the water, then they need to become a liquid water. So the temperature going to change, decrease. That means the heat will be released out. That makes sense, right? Yeah. So that means from the higher temperature state to the lower temperature state, you need to release the heat. Once you release heat, is exothermic process. Okay, so the from gas to liquid, gas to solid, or liquid to the solid, those processes are all exothermic process. Okay, they are releasing heat. The temperature will cool down. Make sense, right? Yeah. So those are releasing heat. So that's an endothermic. Sorry, this is exothermic process. Right? It's an exothermic process, the releasing heat. But if you're from the lower temperature to the higher temperature, then obviously that's an endothermic. You need to absorbing the heat. So those processes need to absorbing the heat. Otherwise, they are not going to happen, right? Just like you boil the water. When you boil the water from liquid water to the gas water, they definitely need the heat from the stove. Otherwise, how come you have the room temperature, you can have this process change? Okay, so this one, they need to absorb heat, which means this is an endothermic process. Make sense, right? Okay, so let's go a little bit more deeper.
And I think you're not sure whether you remember from the gas to liquid. What is the name for this process? From gas to liquid. It's called a condensation. Okay, from gas to liquid, that's condensation. From liquid to solids, that's a freezing. And from gas to solid, that's called a deposition. So those are three process is the exothermic process. Condensation process, freezing, and a deposition, that's an endothermic process. For the another three over here, solid to liquid, this is called a vaporization. From liquid to gas. Oh, sorry. No, I think I write it wrong.
Solid to liquid is a melting. From liquid to gas is a vaporization. And from solids to gas is called a sublimation. So these three process phase change is the endothermic. Okay, yeah, so hopefully you're clear about this. Most of cases is just think about the temperature, right? And you can using the one of the, using water as an example, okay? Temperature from high temperature to low temperature phase, obviously you release the heat. And from low temperature phase to the high temperature phase, you're absorbing the heat. And then you know whether it's an exothermic or endothermic process. Make sense, right? Okay, so let's take a little bit of break. And during the break, please turn in your lab report, 95.
All right, so let's come back. Okay, so the next part. So this is the endothermic or exothermic process. But obviously, we also have the endothermic or exothermic reactions. Yeah, so besides the phase change, that's a process, but we do have the endothermic or exothermic reactions. But generally, it's a similar concept. The exothermic reaction, which means they're going to release the heat after the reactions. Okay, so well, after the reaction, they're going to release the heat. For example, like A plus B, then they're going to form 2C. And then meanwhile, they're going to release the heat. So that is the exothermic reaction. But endothermic reaction is talking about these reactions, we need a heat. For example, like a 2C become A plus B. So during this reaction, we need a heat or we need energy to react it. Without this energy, this reaction will not go. So that is called the endothermic reactions. That makes sense, right? Yeah. So you can think about the heat actually is one of the product or the reactant. If the heat is the product, then that's the exothermic reaction. But if the heat as the reactant, then that's going to be endothermic reactions, right? And also some of the cases, when we dissolve things, when you dissolve sugar, you probably won't see that. But when you dissolve acid, a strong acid and a strong base, like you dissolve sodium hydroxide into a water, when you touch the bottom parts, especially when you dissolve quite a lot of sodium hydroxide, you will feel the solution is a warm solution, which means when they dissolve sodium hydroxide, dissolving the water, actually they're releasing the heat. They're releasing the heat. Okay, yeah. So exothermic reaction is pretty obvious, like you're burning things, right? All the redox not the redox, all the combustion reactions actually is exothermic reaction, right? Combustion reaction, they're producing the heat and the light out. So that's exothermic. But the endothermic reaction is pretty subtle because they just try to absorbing the heat, but in most of the cases you cannot see the absorbing heat, right? So that's a very subtle. I'm going to show one of the demo on the YouTube so you can see what happens for the endothermic reactions.
What I have is some barium hydroxide. Okay, and I'm going to put this into the. In fact, you know what? I'm going to do this in one of the beakers, not that thing, because it's ridiculous. Barium hydroxide, and I've got some ammonium chloride. Now, what I'm going to do is mix these together, and hopefully we should see a endothermic reaction. Yes.
What's with the hand stuff?
What hand stuff?
The hand sanitizer.
Oh, it just lives on my desk. Oh. I was chopping up hearts earlier, and yeah, I need to be not covered in blood. So, what I'm going to do to show how exothermic this is, how much heat this is taking in, I'm going to make this wooden block wet. Okay? Now, you will see why I've done that in a second. So, I'm going to mix these two things together and carefully, I need to break that up a bit. Mix these two things together. Well, hopefully not, because if it's blowing up and giving out huge amounts of energy like that, that would be what type of reaction? Exothermic. Now, we want to see endothermic, so it's going to be a little bit more subtle. So, I mix the barium hydroxide and the ammonium chloride together, and they should start to react.
Does it freeze it?
Well, we should soon see. So they're mixing together. Now, can you see how the consistency of that is changing slightly? It's sort of clumping together, because one of the products it's making is water in this reaction. And you can see actually that's all gone liquid, and it was all just solid powders. It's not milk. You wouldn't want to put it in coffee.
Oh.
Okay, if you put that in coffee, oh, there'll be problems. Now, one of the products of this, because it's ammonium chloride, is it's giving off ammonia, which smells rather horrible. And I'd forgotten about that, which is why I just breathed the huge load in. that sort of horrible, slightly tangy smell in wee is sort of ammonia-like.
Oh, is that what I can smell?
Yeah, that's what you can smell. Unless you've wet yourself, that is the worst smell you can smell. Okay, but also, actually, this is getting actually very cold as it's going along. Okay, now hopefully, if this has worked, it's getting cold enough. Well, you know, I put water on the base there.
Yeah.
Fingers crossed. It's actually frozen the water onto the bottom. Now, this reaction has worked so well, so much energy has had to be taken out of the environment. It's got that water so cold that it's dropped below freezing and frozen onto the bottom. And that is pretty cool.
How cold is it?
Well, I haven't got. In fact, I have got a thermometer. I'm an absolute liar. So I can put that there. That is dropping down to. Well, we know it's below what? 0. So
Freezes at 10.
this thermometer is calibrated to -10. It's shot down to -5 by about now, and it's carrying on going.
Will it freeze our fingers?
If you had it on there, yeah, it would start to. In fact, there's actually ice crystals forming on the side of there.
Yeah, so that is what we talk about endothermic. Okay, so let's see what happens for these reactions. Okay, so now you have a beaker, and then we have the reactions that ongoing over here. Barium chloride and ammonia is the barium chloride and the ammonium. I think it's ammonium chloride and barium hydroxide. Okay, so then they are adding the water underneath over here. So now we call this is endothermic. Then you think about it. What's the system they are talking about? Because you see, we talk about the endothermic and ectothermic is always need to talk about what's the system. And here we talk about this person. This is endothermic. And what's the system we're talking about here? Think about it. The reactions, yes, this reactions is endothermic. So the reaction here as a system, then that means the rest of the others, other than this reaction, are the surroundings, right? Even including the beaker or including the water there or the wood block. So the endothermic reaction is absorbing the heat from all the surroundings, including the air in the outside over here, the air, including the water over there, including the wood block. Okay, so that is why the temperature is dramatically cooled down, okay, around the surroundings, including the water. So water is being frozen. Is being frozen. So that's why they glued the wood block and the beaker together. So that is what happened. So this is endothermic. Okay, remember when we talk about endothermic and ectothermic, you need to think about what's the system it is, right? So for example, let's just give you some of examples. You can think about it. Okay, yeah. When I cooking like a steak, when I'm cooking a steak, for the steak, what's the process it is? What's the process for the steak? Endothermic, right? Then you need to think about, is the steak receiving the heat or losing the heat? Obviously, it's receiving the heat, right? Yeah. Otherwise, you're not going to cook it full. I mean, it's not being cooked. Okay. So, how about the stove? That's gonna be ectothermic because stove keep continue releasing the heat. That makes sense, right? Yeah. So think about that. I'm boiling the eggs. For the eggs, what's the process it is? Endothermic. Egg receiving the heat, right? Yeah. The water, how about the water? We put the eggs in the water, right? So for the water, then that's really interesting because the water is receiving the heat from the stove
and also water is giving the heat to the X. Okay, then that's really depends on what's the surrounding you're talking about. Okay, so system surroundings very important over here. Okay, when we talk about endothermic or exothermic, you need to first think about what's the system, what's the surrounding. Then you can determine, okay, is it endothermic or exothermic. So that's why, I mean, next part we're going to talk about the sign. Sign of the heat. So heat usually don't have a sign, but when the heat transfer, they do have a sign. Okay, so heat usually we're using Q to represent heat. So the negative Q, the Q is how much the Q, which is just a number. The number is how much heat, right? But if it's heat is moving in or moving out, they give you the sign. The negative Q means system lose heat. Or system release the heat, okay? And then think about the system lose the heat, so they have a negative sign because the system has less heat, okay? But if you have a positive sign for heat, that means the system is gain heat. Okay, system losing heat. In another word, the surrounding should gain heat. Gains heat. Loses. Gains heat. And the system gains heat, that means the surrounding should lose heat, loses heat. Okay, so that is the difference between signs. Sign is very important in this concept. Okay, negative sign means is losing the heat. In other words, this is exothermic, right? Negative sign is losing heat. So that means it's exothermic, right? System losing heat, so that exothermic. Plus Q plus, that means it's endothermic because the system gaining the heat, so that's endothermic. Okay, so sign and systems and endothermic, exothermic. Okay, please make this clear. Okay, yeah, next class we also need to talk about this. Last parts I'm going to talk about before you leave is talk about the unit of heat. Unit of heat. Most of the cases we're using the SI unit for the heat is called a joule. It's a joule. But the joule is a really, really small unit. So most of the cases in chemistry, we're talking about a kilojoule, which is a 1,000, right? Kilojoule is a 1,000 joule. So this is usually is a unit that we are talking about, the kilojoule. So 1 kilojoule equal to 1,000 joule. Okay, so that's a unit. But meanwhile, there's other units is talking about the heat. One is calorie. The other one is called kilocalorie. Or kcal. A lot of people writing like this. And a kilocalorie is also be called food calorie. In another word, when you see the label in the back of the food, okay, you see the label, it shows what's the energy, what's the calorie it is. That calorie is the food calorie. It's not this calorie, okay? So food calorie, we know everyone per day average is like a 2,000 calorie, right? Yeah, and the big size person need like a 3,000 calorie, okay? No more than 4,000, okay? No more than 4,000. Well, you can do it, but it doesn't mean you have to do it. Okay, yeah. So food calorie and the difference between calorie and food calorie is just 1,000. In another word, 1,000 cal
1000 calorie equal to 1 kcal, which is the food calorie of there. Okay, yeah. So sometimes you just need to say, okay, I'm getting old, so my digestion is not that well. Sometimes just want to eat something, then you can looking at the label. That's it. Wow, it's only just 1 can of the like a Coca-Cola. It costs like 150 calories. I mean, the food calorie, the kcals. That's a lot. Okay, yeah. I mean, I cannot afford for it. Well, just to let you know, last time I see, if you're just a can, the small can of the Coca-Cola, it will probably like put about like a similar size of the sugar into the Coca-Cola. That's a lot of the sugars in there. Okay, a lot of sugars in there. All right. So this is units for the heat, where most of it we're using kilojoule. Okay, yeah. And the next part, we're going to talk about the unit for the temperature. This is not the topic. We know temperature, we have Fahrenheit, Celsius, and a Kelvin, right? So what is the relationship between those? Let me just draw 3 lines over here, and then we can see the difference. So for this is a Fahrenheit, Celsius, and a Kelvin. Let's see, what is the freezing point for water in Fahrenheit? 32. Okay, 32. So that's 32. That's Fahrenheit. What is the boiling point for water in the Fahrenheit? 212. 212. Okay, for the Celsius, and again, what is the body temperature for the Fahrenheit? 98. It's about 98. I mean, if you think of 97 something, also okay, right? Okay, so for the Celsius, that's a 0 Celsius for the freezing point of water. That's 100 for the boiling point of the water. And generally, Celsius actually is defined in that way. The people, British people just think, okay, define the Celsius. 0 Celsius is the freezing point of water. 100 Celsius is the boiling point of water. Okay, and then for the rest of the temperature is just scaled based on this, and you scale the temperature. Okay, and the body temperature for this is about 37. If you're 36.8, then that's also okay. Yeah, 37 about this. For the Kelvin, that's going to be 0 Celsius is for the freezing point of water is 273, but actually should be 273.15. But let's just ignore the 15. So we just usually do 273. Okay, so 273 Kelvin is 0 Celsius. Okay, and for 100 Celsius is 373 Kelvin. Okay. The body temperature, that's just a 310, and that's it. If we all have a 0 Celsius, we all have a 0. The Fahrenheit, 0 Fahrenheit is not that cold. It's a negative something of the Celsius. But if you talk about a 0 K, then that's going to be completely different story. 0 K is called the absolute 0, which means K Kelvin, there's no more temperature that's below 0 Kelvin. So Kelvin do not have a negative number. Okay, it's just 0 is a starting point. But the absolute 0 is ideal temperature. There's no such object that can cooling down that temperature. Okay, there's no such so we cannot have absolute 0 at that time. Okay, but generally you can predict what is the temperature for the absolute 0. So by definition, absolute zero is talking about at that temperature, nothing is moving, including the atoms, electrons, neutrons, okay, protons. Nothing is moving. So this is at absolute zeros. I think, I mean, the lowest the temperature that we can got in the right now is about like a 4K, but it's already very close to the 0K, but it still have a little bit activity for the protons, electrons. Otherwise, think about it. If everything is frozen, how come you can measure the temperature? Because the digital, all what is that called? All those devices need the electrons moving, right? Otherwise, how come you can measure the temperature? Okay, nothing if it's nothing move. Okay, so this is absolute zeros. Okay, if you talk about absolute zero for the Celsius, it's negative 273 Celsius. For the Fahrenheit, is negative 460 Fahrenheit. Very, very cold. Very, very cold. Okay, yeah. So this is the temperature between Fahrenheit, Celsius, and Kelvin. You don't have to remember this between Fahrenheit, conversion between Fahrenheit and Celsius. But right now, you do need to understand how to convert the Kelvin to Celsius. Okay, so the Kelvin is the temperature is equal to the number of Celsius plus 273 Kelvin. Then that's it. The number of Celsius plus 273, then you will got the temperature for the Kelvins. That's it. It's a pretty straightforward. The commonly, I can show you some of the temperatures. If we talk about liquid nitrogen, the temperature is about 77 Kelvin. Okay, 77 liquid nitrogen. Liquid helium is what we talk about. Liquid helium is about 4K. It's about 4K. We can calculate. We can find, search online. I forgot what exactly the temperature, but 4.15 is about 4K. Okay, so this is a liquid helium is the temperature that we can got. I mean, the lowest temperature generally that we can got over here. Okay, so this is already pretty cool. Liquid nitrogen is 77K. Okay, and it's already really cool. I'm not sure whether you see the liquid nitrogen. It's, I mean, I handle when I do the PhD, I handle quite a lot for the liquid nitrogen because a lot of instruments need to cool down with the liquid nitrogen. And you know, recently there's a lot of computer, then they're cooling this cooling system is a liquid nitrogen. You can just add a very expensive, the cooling system for cooling the CPU with liquid nitrogen. Well, anyway, so this is what we learned for today. Okay, remember what we talk about today. Most of the cases we talk about what is surroundings, what is the systems, and we talk about the endothermic, the flow of the heat, endothermic, exothermic, phase change. What kind of phase change is the endothermic? What kind of phase change is the exothermic? And then we talk about endothermic reaction, exothermic reactions. And meanwhile, we have know the sign of the liquid, a sign of heat. Positive sign means is endothermic, negative sign means is exothermic. And we talk about the joule, kilojoule, food calories, and the Kelvin, Celsius, and Fahrenheit. All right, so we will see each other next Monday. And next Monday, we're not going to making a real lab. Next Monday, in the lab time, I'm thinking about we're going to just do a preparation for the lab 50. So you don't have to making any lab report for the preparation on Monday, okay? And after we prepare the stuff, we will review the exam too. Okay, I think this is very important. All right, let's see you on next Monday. Bye.